In this video, we'll talk about oligopolies. Oligopolies are defined by a small number, but more than one seller, and many buyers. We'll just kind of start looking at two sellers. There are barriers to entry and exit, but they don't limit the market to only one seller, and products may or may not be differentiable. I think often a good example of a oligopoly is maybe you have a small town often near an interstate, and you pull off the interstate and there's only two gas stations and they're right across from each other. Right, so you've got a couple of sellers, more than one. There might be some barriers to entry and exit, but not enough to limit to only one seller. And the products may or may not be differentiable. So in the gas station case, can you tell one station's gas apart from another? Maybe not, other than the branding on the outside. So products might be differentiable, might not. Because there's a small number of companies in the market, we might assume that the choices and the profits of each firm might depend on the choices of the other firm. So this concept is known as strategic interaction, and it's our first look into what we call game theory, or strategic interaction between two or more decision makers. So the first type of oligopoly that we'll look at, or oligopoly behavior between two companies, is called a Cournot, or a quantity competition. In the quantity competition, we're going to have two firms. They're going to simultaneously use MC equals MR to pick their quantity. Based on the quantity that they choose, we find a market price and profit. So in the Cournot, they do it at the same time. Nobody knows what the other one is doing. They're just simultaneous and independent. Right, so two firms, firm A and firm B, are in a market. Market demand is P equals 1200 minus Q in slope-intercept form. And then we're going to say that market quantity is QA plus QB, where QA is firm A's quantity choice and QB is firm B's quantity choice. So we can write the market demand 1200 minus our total market quantity, QA plus QB, distribute the negative 1200 minus QA minus QB. All right, let's pick an easy total cost function, 200Q, so that we can write the profit for each firm, total revenue minus total cost, or PQ minus total cost. So here's market price, depends on both of the quantities. And then the profit function for company A, they only choose QA. So we've got price times the quantity choice of A minus the total cost of producing QA. All right, likewise for firm B, here's our market price times their quantity minus the cost of producing that quantity. Right, I've distributed everything out. So we've got 1200 QA minus 200 QA. We've got a negative QA squared, and we've got a minus QA QB. Right, so there's what we have here. And then down here for B's profit function, we've got 1200 QB minus 200 QB, so 1000 QB. Then we've got a minus QA QB and a minus QB squared. Right, so if you're having trouble defining a profit function or writing it down, anything like that, let me know. Again, we're just assuming that the market price depends on both of the quantity choices for the two firms. All right, so we can write down some profit functions, and we want to know what is each firm's profit maximizing quantity, so that we can find the market price if we know each firm's quantity, and we can find each firm's profit. All right, well, remember that from calculus, the maximum of any function occurs at the point where its derivative or slope is equal to 0. We used that back when we derived the MC equals MR rule. So you can go back into what that would have been chapter 8 if you want to see that proof, or get a hold of me. But what we're going to do here, if we want to maximize profit, we're going to take the derivative with respect to whatever the company is choosing and set it equal to 0. So firm A chooses QA but does not choose QB, meaning that QB is a constant. So when it takes the derivative of profit A with respect to QA, here's profit A. Let's just go term by term. Remember that firm A does not choose B. So this is a a constant. This could be 10, this could be 100. This is whatever QB chooses. Right, so we're taking the derivative of this with respect to QA. A is quantity choice. We're going to get a 1,000 minus, bring down 2 QA to the 1 power minus QB is constant. So we have 1 times QA to the 0, which is just 1, times QB, which is constant. So that's where this QB is coming from. All right, one more time, taking the derivative of A with profit function of A with respect to quantity A to find the optimal quantity A choice, 1,000 2QA minus QB. Right, we set that equal to 0 and we're trying to find, remember, QA. Firm A knows its profit function, wants to figure out what is the best quantity choice. So we take the derivative of the profit function with respect to quantity A, set it equal to 0. I'm going to solve for QA, so we bring this 2QA term over here, add 2QA to each side, then divide by 2. So QA is 1,000 minus QB divided by 2. All right, brought this over here, divided the 2. All right, so what we notice about this is that, in the previous chapters, once we did all of this math, MC equals MR is the same thing as maximizing profit. So if you're more comfortable with doing this, finding MR and then setting it equal to MC, you could do that too, works the same. This, I think, is a little bit faster, all in one step. Maximize profit using MC equals MR to find Q star. But now Q star depends on what the other person is doing, what the other company. If we repeat the steps for company B, right, so now we're taking the derivative of B's profit function with respect to quantity B. All right, so we get 1,000 minus, now QA is a constant, so we get the QA coming along. 1 QB to the 0 is just 1. So this is just a minus QA. And then we got a 2 QB over here. All right, so that's what we've got here. We're going to now try to solve for QB. So we add 2 QB to each side and then divide by 2. We get now that QB is a function of QA. Right, so what we call these are best response functions. Each company knows the market demand and they know total costs. And for now, we're assuming that each company knows that total costs are the same for both. So we can say that each company knows that they have this best response function, which is a function of what the other company is producing. All right, in the coming video, we will look at what happens if there's like some ordering, what if they actually know what QA or QB is before they produce. That might be more common in reality, right? You see some product in the market and you decide to produce some amount of your product. But for now, we're just assuming that QA and QB are unknown, except for that each company knows that their optimal choice will depend on what the other is doing. All right, so let's talk about what happens if they don't cooperate in any way. They can't communicate, they can't talk about what the optimal quantity choice is, but they do know this, right? Each firm knows their own best response function, and they also know the best response function of the other firm. Everything is perfect information right now. So let's consider A's optimal quantity choice here. Q star A equals 500 minus 1/2 QB. And if you're struggling with the math of how we got here, just let me know. I'm happy to do more examples and stuff like that. So what is QB? Firm A doesn't know what QB is going to be for sure, but they know that QB knows all of this information and has this best response function. So if QA can assume that QB will act to maximize their profits, then we know that QB is 500 minus 1/2 whatever QA is. Right, so what we can do is just assume that that firm A knows this best response function. We can plug this best response function in here for QB. And so that's what's going on here. We know that QA equals 500 minus 1/2 QB. We also know that QB is 500 minus 1/2 QA. So QA is 500 minus 1/2, and then we plug in QB here, 500 minus 1/2, 500 minus half QA. Multiply this through, so we got 500 minus 250, and negative times negative gives us a plus 0.25 QA. Right, finally, we want to know what QA is, so we subtract this over here, we combine our constants. Well, we got something we're more familiar with. We get the optimum QA. Right, we could do the same thing. We could we know that QB is 500 minus 0.5 QA. Firm B can anticipate QA is 500 minus 0.5 QB. So they could plug it in just the same. We would get this. Or we also know using the best responses that QB will be 500 minus half QA and get it this way. And given that the two firms have the same demand and the same costs, it shouldn't be hopefully too surprising that in this case, they're going to produce the same quantity. Right, what about market price? We know that market price is 1,200 minus the sum of the quantities. Then finally, we can find the profits for each firm. Price times quantity minus total costs. Right, so the profits here are positive. We can infer that the firm would rather produce than shut down and produce Q equals 0. So why is this a non-cooperative solution? Well, first of all, each firm must be correct in believing that its competitor will choose Q star. And in some cases, that's not true. So for example, like companies like Walmart have caught some flack before for increasing their quantity above this level so that competitors' profits are negative to drive them out of the market. All right, so here we've assumed that each company knows the other's best response function, which we derived. If each company is acting to maximize profit, then they'll make this choice. We can plug in and solve. But we have to address the case of what might happen if a company did not act to maximize profit. They acted to with some other goal in mind. Right. So in the next video, we'll talk about cooperative behavior. What happens if they form a cartel or are allowed to communicate in some way to maximize profits.